Well, welcome to the meeting number 14 in the Computational Chemistry class. Thank you for finding time to come here. And there is one novelty in organization. We are trying video streaming. If everything is working, those who will click on this link should see the same video we are doing in class. But I have no control of whether it works. We will try. So, few organizational moments before we go to the actual material. So, I am supposed to distribute few pieces of material. Everyone did great on the homework. So previous one and the recent one, I've got couple in printing and couple of emails. So please consider to send them as an email if you prefer. It is fine. What we will be doing very soon is presentations based on what we are doing in labs. So we are complementing our effort in getting the theoretical background for computational chemistry with practical skills. And these practical skills could be memorized in better form, or we can understand them better if each of you select one of the subjects and present to others. So one is becoming a master of one skill and teaching others and sharing the history of success and failure, so that the rest of the class teaches not on his or her failures, but on the success and failure of one. And last time when we met, there was a democratic procedure of choosing your preferred subjects for presentations. I was trying my best to follow your choices, and if you do have any objections, you can quickly tweak it. You can take it down. So basically it summarizes what we were doing on previous couple of labs, and the list of skills here, upon completion of presentations, you will become certified quantum chemist who can do most of the practical assignments of characterizing atomistic models of real materials with one selected method and one selected software. So you are not getting too many of tools, but core set of tools that would work for almost anything. From the time of this presentation until the rest of the course, we will be incrementally improving our arsenal and going deeper into possible list of skills. I do have two options that I will need your opinion by emails or just by everyone answering yes, no. If you want to complete the course quicker and go into deeper materials, we can arrange these presentations in coming Thursday, but it will be a little too early. And I wouldn't mind if we do it one Thursday later. You wait a week and do it then. So do not answer right now, develop your opinion and share it with me privately or by emails. I'm happy either way. So, what is our goal? What is the material that we are going to cover? When we were meeting last time, and suppose we've forgotten what we were doing, we can look online and just look the recording. We were getting final set of components to launch our reaction, so to say, of building Hartree Fock method to compute electronic structure of any material. So right now we have our workbench with all components, and today we are going to fuse them together and get the method. If you would call ourselves theoreticians, from now on we would start sitting with abacus or calculator and doing calculations with pen and paper. But no, we are not going to calculate anything. We are just learning the algorithm, and our goal is to be educated enough so that we can provide this algorithm to a computer scientist who, for reasonable payment, will program this code and allow us to compute properties of materials. Hopefully this method was programmed a long time ago and we can immediately run it, immediately practice. So when we met last time, we got the concept of how to go from orbitals to total energy, the contributions to the total energy from electron interaction, the symmetry influence onto the shape of wave function due to Slater determinant, and we started discussing how to build one electron Fock operator. So our main compass, our main navigation is to reduce terribly complicated problem of multi-electron problem, and all molecules except H2 plus are multi-electron atoms and cannot be solved by pen and paper. So because of the number of degrees of freedom, now we are substantially reducing number of degrees of freedom. We are reducing multi-electron problem to one electron problem. And we already got an idea how to do it. Now we need to more rigorously set up a protocol, how a computer will do it for us. So today we will go through these components, fuse them together, and at the end of the meeting we will do so-called, well, one more name in the list of names. So before we were dealing with Hartree and Fock, now there is one more guy, Roothaan, who set up this equation in such form that it can be very, very efficiently computed by the computer. Any questions on this overview? Good. What I'm going to distribute. I'm going to distribute few pieces of handouts more that you do not need to read them carefully. You can use it as scratch paper or utilize it. For example, one of the handouts is a next homework for coming Tuesday. This is really quick. You can do it in 1 minute by the end of this class, if you listen carefully. And I will not give comments on what it is and how to do it, because it will just launch your attention.
I have a feeling it's a flowchart, right?
Yes, it is a flowchart. And during the meeting, we will get some equations that are being processed in the RAM of the computer when a computer is solving Hartree Fock equations. And when you sit in silence at home, you can just fill these boxes, set up arrows between them, and when we meet in a week from now, we will see whether it is same as in textbooks or a little different. Okay, what else can I hand out? Second opinion. If you do not trust me, but you trust in computational chemistry, and you do want to have some reference point or another source of the same information. So here is the printout of 2 pages from a book that very briefly summarizes what we are doing. So this is not just a book. It is a book issued by the developers of the software that we are using. So it is expression of the equations in such form as they believe in and as they use for actual computations. Okay. And I have one piece more, which is more entertaining. Can't control. Okay. As we go through the meeting, I will either show you pre-recorded slides, or if they are too long or too boring, I will go to the Blackboard and comment them or derive something by hand, just so that we have an opportunity to discuss it. Because showing slides one by one is a little... I would fall asleep if someone shows me slides. So here is the list of subjects that hopefully you will present. And I hope that I didn't offend anyone by putting a wrong subject. And here is an overview of the course. So the oral course consists of 4 chapters: molecular models and geometry optimization, simplest theory for exploring structure, Hartree Fock theory, then most popular density functional theory, and then all possible theories for excited states. So approximately equal spreading. And today we are approaching close enough to completing the chapter on the Hartree Fock theory. So we are casting it in the matrix form. If you do presentations on Thursday, we will follow the schedule. If you postpone it, we will be a little swap between presentations and start of the new chapter. But I do not see a very big problem in this. So what do we have here? We are going to have additional look on each of the 5 components of the Hartree Fock theory, which we covered last time. So they are Coulomb operator, exchange operator, Fock operator, the new concept, but it is very simple, overlap matrix element, and electron integrals. So they all 5 talk about the same thing from different angle. and we better focus on them as they are mostly challenging. The rest of the supplementary concepts should be easy. And before we look on them and merge them together, we are going to focus on the concept of basis sets. Some of you will also cover it in the presentations, but before we were believing in or we discussed and agreed on the following paradigm, that we start with atomic model, then we assign atomic orbital, same as for hydrogen orbital, hydrogen atom for each atom, and then on the basis of atomic orbitals we build molecular orbitals, plug them into Slater determinant, find total energy, and if they are not good enough, we fill them back into the equation for molecular orbitals and repeat it again. But the key missing part in this schematic that we didn't discuss what are atomic orbitals in details. We agreed that they are something like hydrogen atomic orbitals. But we may throw a little more detailed glance on the explicit mathematical expression for atomic orbitals before we go further. And this will be not exhaustive. I will try to show very brief scheme through, sufficient to get the overall idea. So before we start exhausting ourselves with math, let's show that all theories have a human component. So it is, the theories were not designed to torture young people. The theories were designed with purpose to describe properties of materials, and they were derived by real humans who were living, drinking, maybe eating, and their biographies are available through Wikipedia. So, a couple of meetings ago, we were discussing what would happen in the world if we would not have Fock, if we would have the Hartree theory. Then we would not have the exchange term in the energy, and the overall total energy of any molecule will be tending to be unstable because of the antisymmetry principle. But still, it is main step from multi-electron wave function to single electron equations made by Hartree. And the critically important component of the bringing in antisymmetry principle was done by Fock. So here are his dates, name, and my little connection to him, that one of his graduate students who defended thesis in 1937 was my college teacher. I was in the last year taking a class from him. I cannot say that I was the best in the class, but at least there is a little connection. So, okay. So our goal is to say more detailed information, more detailed analysis about the atomic orbitals or something that does replaces them. And atomic orbitals are needed because by making a superposition of atomic orbitals with coefficients that we are looking for, we are getting molecular orbitals that will form overall wave function, and that you can happily plot using Gauss-U software. But what are these chi sub A functions? The little problem with them is that they do have discontinuity. They have spikes. And mathematicians hate any functions with discontinuities. They cause problem. So good mathematical function that doesn't have discontinuities, doesn't have division on zero. So everything changes continually. I'm going to skip all boring factors and show only the leading terms. So if you do have ion at position R1 and you have S atomic function of the first electron around this ion, it will look like exponential that decays as absolute value of distance from electron to the ion, right? And this function, so what is exponential value of exponential at argument equals 0? E of 0 equals, what? So, then it has non-zero slope. Goes to the left and to the right. And actually it is a three-dimensional figure, but here is the sharp spike. If you would try to represent such function numerically and perform integrations, convolutions of function like this, this will create unnecessary complications. And the main idea, main little step that made it possible to go forward and do a lot of numerical computation is to approximate this function by e plus r1 plus r1 lowercase to the power 2. So we had power 1, we change it to power 2. So it is the function that rapidly decays as we depart from the position of ion. It has some disagreement with actual hydrogen atomic function in the vicinity of ion. But for any mathematical operations of taking derivative, multiplying such functions by each other, by integrating them, one can get an analytical answer and make a predetermined answer of such mathematical operations as a part of the code. So we replace 1 with 2. So from power 1 to power 2. Instead of exponential, we are getting Gaussian functions. And this is the reason why the piece of software is called Gaussian. Everything what we do could be possible with atomic functions as well. But then it would take like 100 times longer and not as efficient. Or maybe even longer, because one need to redo a lot of operations in explicit numerical form. While here, a lot of operations that are done to basis functions can be computed analytically and pre-recorded to the software. Good? Make sense? What else? Atomic Gaussian. This is not all. basically, at basis is our free parameter. If you have a very large set of functions that do not coincide with each other, for example, here it could be functions centered on other ion, or it can be a function that represents p orbital, x times p. Those atomic orbitals can work as the basis to express molecular orbitals. Any complete set of functions can work instead of atomic orbitals. But if we are working with small molecules, with electrons localized around ions, atomic light basis is good. But there is a different limit. There is a different limit when this one is not the best. For example, we have a periodic crystal. When the atoms are arranged in a periodic lattice with a repeating pattern. And then the leading feature of the system is not where the atom position, but the fact that they are repeated again and again at the same place. Then instead of form that is localized on the ion, one can use a form of a plane wave. Here we are showing only the real part. So it definitely will not be localized on a specific ion, but if we add together plane waves of different period, we can reproduce any function, any molecular orbit. It will be bordering with the concept of Fourier transform, on one hand. On the other hand, it will help for electronic wave to go from one unit cell, one piece of this periodic pattern to another periodic pattern, and repeating the same image again and again. So right now, we are dealing with the codes that are focused on small chemical molecules, with bases centered on atoms. But in the second half of the course, we are going to cover another piece of software which is designed for periodic solids. And then instead of atomic functions, instead of Gaussians, there will be plane waves. And we are not fighting for rigorosity here. If one would, there will be coefficients here, there, and it will be a little bit more complicated expression.
How big do the solids have to be before you start seeing the plane wave behavior? How big do the solids need to be? Could you do like a quantum dot or nanocrystal lead size thing, or do you actually have like X-ray diffraction size crystals?
We will be able to do both.
Okay.
But for quantum dots, one doesn't need the trick with plane waves. One still can deal with atomic basis. But if we are focusing on true periodic infinite bulk, then one definitely cannot live without those plane waves. What was here? Oh, the same as on the board. So atomic can be replaced by Gaussian from 1 to 2, and in the periodic solids one can use plane waves. Good. Now we are coming to hardest part, to review Coulomb exchange and fuse them together into actual equations. And the goal that we are pursuing, the goal that rests on our choice of orbitals, is to build set of equations for expansion coefficients that allow to build molecular orbitals as a superposition of basis functions. Before we were telling as a superposition of atomic orbitals, now we can tell as a superposition of basis functions. That can be whatever. Equations for these expansion coefficients. And these coefficients should include a feedback of the background electrons to our electron of choice, electron number 1. So there will be influence of background electron. It will take into account antisymmetry feature. Everything will be condensed in so-called Fock operator that does replace Hamiltonian. It will be operator for which we can find eigenstates, and those eigenstates will be molecular orbitals. And then this Fock operator will include contributions from the rest of electrons. So two terms will correspond to electron-electron interaction, Coulomb and exchange. So Coulomb, if we go from total energy to one electron operator, then we are putting our electron number 1 away, and the rest of electrons are staying in the Coulomb interaction operator. So it is density of this background electrons divided by distance from the point in this field of background electrons to our number 1 electron of choice, integrated over all positions of the background charge, and then this is as a one thing, as an operator that acts on electron with this index at this position. If we borrow picture notations from multi-electron theory, from Feynman diagram, then background electrons is an additional arrow. So electron is an arrow, interaction is wavy stuff, but now we do not care what they are. We are closing the previous picture by the black box, and we are considering that this operator is an unknown black box that converts wave function of first electron into a function of the first electron, maybe a little bit changed. So kind of scattered at position R1. And position R2 are integrated. So this is a pictographic representation of Coulomb operator. One electron operator that will help to build molecular orbitals. If we are trying to do the same thing for exchange operator that originates from antisymmetry property of multi-electron wave function, then we can cast it in a specialized form for one electron equation. The exchange operator acting on the orbital, let's say orbital number 1 at position 1, can be cast as in this form that doesn't have direct intuitive explanation. So it is the same procedure as we did before for pure Coulomb. This replacement of one orbital from this background density to the orbital that we are playing with. So we need to introduce this exchange. And it can be interpreted that we are applying this background field to orbital number 1, but suddenly it converts into orbital number 2 that was somewhere in the background field. What is important that the sign of exchange term is negative, and it helps to increase stability of the molecules. What do we do next? We need an equation for molecular orbitals. And it will look very similar to Schrödinger equation for one electron. It will have kinetic energy acting on this electron, potential energy that includes attraction from backbone of the molecule, attraction to all ions, and the Coulomb and exchange terms contributed by all but one electrons, forming a background. So kinetic, potential, Coulomb repulsion, and exchange, so to say, attraction. Or attraction is not the right word. Piece of energy with negative sign that stabilizes the molecule. And this will be one electron operator acting on one electron wave function that we need to find eigenstate of. We are almost done. We are done with all fundamental parts. But there are devil is in the details. There is a detail that is important if we choose to work with molecules and with atomic bases. Typically, when we do calculus, math, Fourier analysis, we analyze set of basis functions, and we say that they need to be continuous, and they need to obey. The word starts with letter O. Yes, orthogonality. So if one multiplies a function by another function from the if one multiplies the function number 1 from the basis set to wave function number 2 from the basis set, they should give 0. Right? It is what we typically expect in all programs. So product and integration of two good functions should be either 0 or 1. But if we do have these two functions which are centered on different ions, R1, R2, it is like two mice that have tails, and they tease each other, they touch each other with these tails. So this little overlap of the basis functions will be non-zero. So the general expectation of the orthogonality is wrong. So for atom-centered basis functions, orthogonality is not maintained. Make sense? It is a little technical details. We can take care of it really simply, but we cannot forget it. So indeed it will be 1 if they overlap, but it will be a specific number that corresponds to the extent of their overlap. And one doesn't need to design smart words. If they overlap, then this S will be overlap integral. Overlap integral. Good? Now, we need to recast Hartree Fock equations with an account of the non-zero overlap integral of the basis function. That's it. That's it. After we are done with it, we can go home. A little boring notation that we do not actually need for our practical life, but we better skim through really quick. If you are tired, you can make a little break. What I'm going to tell right now is not a critical part of our story. So I will give you a signal when to wake up. This is important only if you have a plan to go from applied science to methods development. So the terms for 2-electron interaction in total energy are cast as the integral including 4 wave functions. And these wave functions are differed by 3 different things. Whether it has or it doesn't have star, at which point of space it is evaluated, and what is the index of basis atomic orbital. If you want to make a general notation, if you want to practice laziness and avoid writing these integrals again and again, we can agree on the order of stars, order of position in space, and vary only indices of orbitals. So let's say first 2 orbitals will be evaluated at the same position in space, 1. So here is 1, and here is 1. Good. Second pair of orbitals will be evaluated at position 2. Here 2, here 2. Good. And now we will alternate stars. Star, no star, star, no star. So that it will be kind of density, Bryant cat, and this will be kind of Bryant cat. And then instead of pulling this long expression, this integral, we can make round brackets and give the indices of orbitals. Like alphabetically RSTU, RSTU. Keep sleeping, it is not important. So, who needs and what is the benefit? If we want to express either Coulomb or exchange contribution to the total energy, we will just put the same brief shorthand notation and just change the order of indices. So if 2 first indices and 2 second indices coincide, it will be Coulomb. If they are alternated, it will be exchange. If same notation is practiced in the little handout that you have. And they do not explain it. They believe that everyone who starts running Gauss U knows this abbreviation. Okay, no challenges. It's like when we running in sport, we are seeing what is the finish. So you can speed up and complete it. Right now, we understand that we need to solve one electron equation for molecular orbital, where the Fock operator includes all this enchilada. And we are going to take into account that molecular orbital is not a function of position in space, but it is an expansion over basis functions. And then any function has discrete number, it is a vector in space with infinite number of dimensions. And we want to deal with finite number of dimensions. So we are going from continuous to discrete. It is so simple that I can probably do it on the blackboard. I raised this mice. Four operator acting on the orbital. I get energy. And now our molecular orbital is expressed as a summation. Molecular orbital number I is a summation of basis functions number mu group with expansion coefficient that includes both number of molecular orbital and number of basis function. Basis. Just plug in this expression into this equation and see what happens. Summation u chi u epsilon sub I summation u c u. So we want to erase basis functions. We want to erase these functions that depend on continuous variation. We want to keep equation only for discrete coefficients. And how do we do it? I know that at least two people in the audience are very impatient to suggest how to do it. If those are ket vectors and we want to get rid of them, we need to use either orthogonality or what replaces it, multiplied by bra here and there, and get rid of functions. Keep only numbers. If we are in continuous representation, we add integral chi star u r dr. F summation c I u. Oh, please wake up. This is important. Stuff before was not as important. This is important. This is what we will be actually doing. Or what computer will be doing for us again and again. Equals target energy of molecular orbital integral dr chi star u r summation u c I u chi u. Any objections at this point? Very good. I'm going to pull the summation sign up front. And here I'm also going to pull summation sign up front. Then here we will have expression integral d chi mu star f, which is operator, one electron operator, chi mu. So if you do have wave function conjugate, operator, and wave function with an operator in between, this construction always gives a number. So we are getting rid of wave functions, whatever they are, and get a number. But since there are two different indices, the value of this number will depend on the indices. So it will be an object with two indices, mu and mu. Object with two indices is a matrix. So it will be matrix element of the Fock operator. Good. Here, what do we have on the right side? We do have integral dr chi star u of r chi without star mu of r. This is our old friend from 10 minutes ago. If chi will be good functions, it will be Dirac delta. It will be either 0 or 1. But since they are bad functions,
Overlap.
huh?
Overlap.
Yes, correct. Overlap integral. Let's call it S mu. So we replace this integral by this matrix, and we replace this integral by this matrix. Do we have any integrals or any wave functions left in the expression star? No. So we eliminated any integrals and any continuous functions. We formulated everything in terms of matrices and expansion coefficients. Let's just summarize what we did. Here's the camera. So we have summation over mu. Then we do have matrix element of Fock operator. Mu. Right? So it replaces this, this, and this. And what we have left is only this coefficient, C sub I sub u. And we are done with the left part. Good? Now let's deal with the right part. So we got rid of integral and the wave functions. But we still have the summation over u. We have eigenenergy at the front. And we do have S mu u times Ci mu. Any objections? Good. We are basically done. I'm just going to exhaust your patience for a couple of minutes more to recast it in the more pleasant form. This is correct. This is acceptable for programming for the computer. But we do want to do it a little bit more practical and easy to accept and comprehend. how do we formulate the matrix by vector product? Row by column, and once again row by column. Should I? Does anyone wants to practice it? Okay, you can do it as a next homework.
F11 times C1 plus F12
Okay.
times C2.
F12 C2.
And then F21 C1 plus F22 C2.
Good. All correct. But suppose that we are so lazy that we do not want to repeat it again and again. How can we replace this expression in form of in this form as a sum? So see the index 1 here in the matrix and in the vector are repeated. Index 2 in the matrix and index 2 in the vector are repeated. Why don't we write C summation over nu going from 1 to 2, F1 nu, C nu, right? So matrix per vector can be replaced by summation, where one index should coincide. Do you see it here? Yes, we do. Nu here, matrix, vector. Nu here, matrix, vector. So what does it mean? That for each number I, for each index of molecular orbital, we are looking for a vector of expansion coefficients. C I nu equals 1, C I nu equals 2, C I nu equals 3. Right? And this vector is being affected by a matrix of matrix elements of Fock operator and by a matrix of overlap integrals. Good? Just a tiny bit to complete. So matrix, this will be C sub I vector of expansion coefficients. And F, let's make it flat. F1, F1, 2, within F21, F22. So matrix of matrix elements will be Fock matrix. Fock matrix. I'm going to reserve a last piece of space that I don't need anymore. So we multiply Fock matrix by vector of expansion coefficients, and we are getting eigen values, matrix of overlap acting on the vector of expansion coefficients. So this is the equation that is being by Gaussian when you write Hartree Fock, with a little addition that it is solved in a self-consistent manner. Any objections? Any questions to this expression? Okay. So, same as we practiced on the board. So we plug in explicit value for expansion over atomic basis. We plug in, we take into account that we do not have orthogonality, we have overlap matrix element. We plug it into equation for molecular orbital, and then we recast with multiplying by bra. We recast it in the form where we have matrices, so matrix element here, and vectors, matrices and vectors. So, Fock matrix, vector of expansion coefficients. Overlap matrix, vector of expansion coefficients. So here is the vectors, matrices, and then the equation for molecular orbital originating from Hartree Fock theory written in the matrix form changes its name. It converts from Hartree Fock equation into Roothaan equation, who first decided that, okay, let's be practical and think about atomic orbitals. And as any equation for, as any eigenvalue and eigenvector matrix equation, it can be solved by pulling left and right parts on the same side, finding determinant and making it equal to 0, and then finding the set of eigenvalues and eigenvectors. Good? We will need to talk about this detail one more, but here is the flow chart of what we expect, how we bring everything together. So as humans, we start with positions of ions. Then we need random numbers for initial guesses of the molecular orbitals. And then we use them to form Fock matrix that needs some knowledge, about basis. And then with diagonalizing Fock matrix, one is getting set of molecular orbitals. Then from molecular orbitals, one obtains total energy and checks whether it satisfies conversion criteria. If it does, we print output and analyze it. If it is not, it feeds back the expansion coefficients into formation of new Fock matrix. And then one repeats this cycle again and again. That's it. Right now, it is your chance to express any objections to Hartree, any objections to Fock, or any objection to Roothaan. If not, I want to say thank you for the patience. It was number 2 hard lecture. Number 1 was about Born and Oppenheimer. This is the second in hard. See you on Thursday. We will not be in the no lab tomorrow. Just prepare for your presentations. Meeting is dismissed.
So we are presenting on Thursday or following Thursday?
We are